we are performing the design of battery management system. Uh, so basically, uh, a battery management system is a combination of hardware and software that controls the charging and of cycles, discharging cycles of the battery. It even logs some important parameters that helps in determining the state of charge as well as the battery life. So in front of us, we can see the typical BMS, which consists of cells which are in combination of series and parallel. It also consists of cooling system, along with which it consists of a contractor and pack measurement. It also consists of a host application control computer. So basically the BMF will control the recharging of battery by redirecting the recovered energy back into the battery pack. A BMS may monitor the state of the battery as represented by various items, which is voltage, temperature and current. So basically we are saying that the input to the BMS will be voltage, current and temperature. So a battery management system can comprise of many functional blocks including cutoff, FETs, a fuel gauge monitor, cell voltage balance, real-time clock, temperature monitor and a state machine. So here in the diagram we can see is that there is a MCU which controls the BMS. There is a current amplifier. There is a cell balancing circuit, and there is a temperature sensor to measure the temperature. So basically, it consists of the grouping of the functional blocks varies widely from a simple analog front end that offers balancing and monitoring. Further, we are going to look that the BMS, the important hardware which consists of BMS in which consists in BMS is LTC 6811. So the LTC 6811 is a multi-cell battery stack monitor that measures up to 12 series connected battery cell with a total measurement error of less than 1.2 millivolts, and it also takes 290 microseconds to measure all the cells in the system. It also synchronized voltage, and it is also used for synchronized voltage and measure current measurement. It is configurable as a I2C or SPI master. The LTC 6811 includes battery passive balancing for each cell with individual PWM duty cycle control for each cycle. So further, Harsh Dankara will explain the hardware system.
So this is the balancing circuit of a BMS. So during the charging and the discharging cycles of the battery, the voltage value for individual cells may vary. So this leads to unequal voltage levels in the cell around the battery pack, which will further degrade the battery life. So a cell balancing circuit is an important factor for to keep the battery working efficiently. So the balancing circuit consists of a 10 ohm bleeder resistor. So bleeder resistor is just used for the purpose of discharging the electric charge stored in power supply, and it consists of p-channel MOSFET and an optocoupler to drive the p-channel MOSFET. Next, for temperature sensing, we are using thermistors. So thermistors are passive components that respond to change in temperature by changing their resistors. So the temperature sensor we have used is PANR 103395. So it is a NTC type, a negative temperature coefficient, which means that whenever the temperature, whenever the resistance decreases, the temperature increases, and vice versa. And also, it has very good stability and faster response time. So we have opted to use this part for temperature sensing. This is a cell model. So the cell model can be represented by an equivalent circuit, which has an open circuit voltage, a resistance which represents internal resistance, and a resistance and a capacitor in parallel. So right side we can see a graph where after supplying current, the voltage drops, and first gradually and then sloping. So the gradual is because of the so gradual is called as the static drop, and The sloping is because of the dynamic thing of the circuit. So dynamic is because of the resistor and capacitor in parallel, and the static is because of the internal resistance of the battery. So this slide will be explained by Parth Sanil.
To obtain the cell characteristics, we have designed an electric load which can discharge with different current and profiles. The circuit we have designed uses 1 ohm and 10-watt resistor to dissipate the cell's energy in the form of heat. The cell current and voltage is monitored and stored. The circuit uses an STM32 development board for control and monitoring the process. A PID controller is also implemented, which adjusts the duty cycle to maintain constant discharge current. When cell is fully discharged, the process is halted, and the same setup is also used for charging of the battery. The cell was subjected to a constant current discharge of 0.4 coulomb and 0.75 coulomb. The terminal voltage and charge discharged AH were monitored until the cell reached the lower voltage threshold. It is evident from the test results that the capacity of the cell is a function of discharge rate. The total capacity of 2.6 is 2.6 AH as specified in the datasheet. Accurate battery models are vital in development of algorithms for SOC estimation. The SOC estimation, there are methods such as open circuit voltage measurement and current integration, which are reasonably accurate, but for measuring SOC of modern battery chemistries, we used extended Kalman filtering, which is extremely accurate in the SOC calculation. We use Simulink to simulate the battery SOC. So, Simulink has an extended Kalman filtering block that takes the cell voltage and current as input and has a recursive algorithm that calculates the SOC of the cell as seen in the graphs. This is the MATLAB simulation of. Thank you.